Welcome to a deep dive. Today, we're tearing apart a piece of technology. It's become really essential for sending live video, other time-sensitive data over the internet reliably and with surprisingly low delay.
Yeah.
Our source for this is a pretty deep technical overview of something called SRT, Secure Reliable Transport.
The internet, it's amazing. Connects everything. But from a technical view, it's kind of messy.
Messy.
Yeah, packets take different routes. They can arrive late or out of order. Sometimes they just vanish.
Right.
For email, loading a website, that's mostly okay. Protocols handle it. But try sending a live video stream like that,
Oh, yeah.
where every single frame, every millisecond of delay really matters, that unpredictability.
Right.
Huge problem.
You absolutely can't have your live broadcast just drop frames or freeze because the network hiccuped. And traditionally, fixing that meant super expensive stuff,
Yes.
right? Dedicated connections.
Exactly. Think satellite links, private fiber, big bucks. But the public internet is just so much cheaper,
Yeah.
way more accessible. And that's the sweet spot SRT was designed for. It basically builds this smart, robust layer right on top of UDP.
UDP, User Datagram Protocol. The fast one.
Super fast, yeah. Fire and forget, but totally unreliable on its own. SRT adds that reliability piece without, killing the speed you need for live stuff.
Got it. So it's adding smarts to UDP's speed to kind of tame the Wild West of the public internet for live applications. And this wasn't built from scratch, was it? I think the source mentioned.
No, not at all. SRT actually grew out of an earlier protocol called UDT. UDP-based data transfer protocol. SRT took that foundation, which was initially designed more for bulk data transfer, like files,
Okay.
and made some really crucial specific changes, tuned purely for the demands of live streaming.
Okay, so let's start right there then. What was UDT doing, and what was the fundamental problem with using that approach for something like live video?
Well, the main challenge is just getting those low latency video streams, maybe MPEG-TS, from A to B with minimal delay on a perfect network, maybe inside a building.
Yeah, controlled environment.
You might just use raw UDP, maybe add some basic forward error correction FEC for tiny glitches. UDP's fast, like we said. No overhead waiting for acknowledgments or anything.
But then you take that same raw UDP stream onto the public internet.
And bam, you're suddenly dealing with real packet loss
And,
wildly varying delays, jitter.
right, big problems.
Exactly. And the old solutions were pricey. Some early attempts to add reliability over the internet using protocols meant for bulk data, they often needed huge amounts of extra bandwidth just for recovery.
Which totally defeats the purpose of using the chip internet in the first place.
Precisely. Now, UDT, it's an ARQ protocol, automatic repeat request.
Okay.
It was designed to use maximum network capacity by making sure everything eventually gets there. It prioritizes retransmitting lost packets.
Sounds good for files.
Great for files. Terrible for live video in its original form anyway.
Why? Because if packets got lost, UDT would just keep trying to resend them, blocking new data. Is that it?
That's the absolute key problem. UDT's congestion control could end up prioritizing sending old lost packets from this loss list.
Uh-huh.
And that could block the application's API.
Uh-huh.
So your video encoder, it might have brand new frames ready to go right now,
Yeah.
but the transmission queue is clogged, full of old lost packets being resent. The application, your encoder, would just be forced to drop those fresh, timely frames.
Oh, wow. That's completely backward for live. You'd much rather drop an old packet that's already missed its moment than a brand new one that's perfectly on time.
You've nailed the core insight. This is where SRT gets really, really interesting. It fundamentally changed how UDT4 behaved, specifically for live streaming.
How so?
Instead of just blocking the API, it actively tries to share bandwidth between the real-time packets coming in now and the retransmissions of lost ones.
Yeah.
And crucially,
Yeah.
it's willing to drop older packets right out of its own send buffer.
Yeah.
They've been sitting there too long and just can't possibly arrive at the receiver in time to be useful for the live stream.
That willingness to sacrifice old data for timeliness, that's the game changer for live, isn't it?
Absolutely. It prioritizes the now.
So what were some of the other specific technical tweaks SRT made to UDT4 to make this happen? The source mentioned a few.
Yeah, several really smart ones. They changed how buffer sizes are configured and measured. They started using milliseconds.
Not bytes or packets.
No, milliseconds, which is brilliant, actually,
Yeah.
because it lets you set your desired end-to-end latency directly. Doesn't matter what the video byte rate is.
Yeah, that makes total sense. Latency is time, not data volume. Much more intuitive for the user.
Completely. They also added vital things like timestamps to control packets. That wasn't always properly implemented in UDT4.
Ah.
And they built in a mechanism for timestamp drift correction, between sender and receiver clocks over long sessions.
Right, clocks drift.
Another big one was how missing packets get reported. UDT often used timeout-based retransmissions, which could get very chatty and use a lot of bandwidth.
Oh.
SRT switched to periodic NAIC reports, negative acknowledgments. The receiver regularly sends a compressed list of exactly which packets are missing.
So the receiver tells the sender what's gone, on a schedule, instead of the sender guessing based on timeouts.
Much more efficient for a constant stream, yeah. The source says this NAIC report happens roughly every half RTT round trip time with a minimum floor of 20 milliseconds.
Gotcha.
And finally, they added timestamp-based packet delivery TSB-PD at the receiver. This gives the receiver really fine-grained control over pacing packets out to the application buffer. Ensures smooth, consistent playout.
So SRT took UDT's reliability idea but totally re-engineered it, with a laser focus on the time aspect.
Right.
Critical for live streaming.
Exactly.
So how does it combine these pieces then, getting both reliability and low latency in practice?
It really comes down to its core packet handling and the buffer management. You've got data packets carrying the stream itself.
Right.
And control packets doing all the behind-the-scenes work. Acknowledgements, retransmission requests, flow control, all that jazz.
And the reliability part hinges on those ARQ things, the ACKs and NX.
Exactly. But adapted for the live situation. The receiver sends ACK's acknowledgements back to the sender, tells it which packets arrive safely using sequence numbers.
Like, got everything up to packet number 100.
Pretty much. An ACK for packet N+1 means everything up to N is safe, which tells the sender it can free up buffer space.
Okay.
SRT uses different kinds of ACKs. There are full ACKs sent on a timer, like every 10 meters by default. They carry extra info, like the current RTT estimate. And light ACJs, often sent after a certain number of packets, maybe 64, just the sequence number, good for high byte rates.
And then NX, negative acknowledgements?
Right. For the missing packets, like we said, they're sent periodically in a compressed list. But here's another smart bit. If a packet arrives way out of order, say packet 10 shows up, but 9 is still missing,
Yeah.
the receiver doesn't wait for the next periodic report. It fires off an NAC for packet 9 immediately to speed up the recovery.
Makes total sense. Chase down that missing one right away if its buddy has already arrived.
Exactly. The sender uses these NACs to build a loss list, and it prioritizes resending those missing packets. But the real magic, where reliability meets low latency, that happens in the buffers, especially at the receiver.
The buffer latency, the millisecond setting.
That's the one, the configurable SRT buffer latency.
How does that connect reliability and latency again?
Think of it like the source describes it. A sliding window on the receiver side. Packets arrive, they get held in a buffer, but they don't get passed to the application, your video decoder, until they slide out of this defined latency window.
Okay.
This window is the strategic time cushion.
So the receiver deliberately holds onto packets for, let's say, 200 milliseconds, if that's what I set the latency to.
Precisely. That 200 milliseconds is the maximum time the whole system has to.
Right.
1, detect a lost packet. 2, send a NAC. 3, have the sender retransmit it. And 4, have that retransmitted packet arrive before its scheduled playtime within that window. If the retransmitted packet makes it in time, great. Insert it seamlessly. If it doesn't make it before it slides out of the window.
Too late.
Too late. It's dropped by the receiver. Skipped.
That's the key. The latency isn't just delay for delay's sake. It's the recovery budget. And if you can't recover within budget, you sacrifice the packet for timeliness.
You got it. And this leads directly to that TLPKTDRP concept.
Oh.
Too late packet drop. The receiver drops packets that miss the deadline.
And the sender does this too, doesn't it? To avoid sending stuff that's already doomed.
Correct. The sender also respects this latency window idea. It will drop packets from its own send buffer if they're so old they couldn't possibly arrive at the receiver and still be useful within that receiver's configured latency window.
Smart.
The source does note an exception, though, for really big packets like parts of a video iframe. They get a minimum hold time in the sender buffer, maybe 1 second, even if the configured latency is lower. Just a little safety net.
Okay. But generally, don't waste bandwidth sending packets that are already past their prime. Makes perfect sense. Now, all this timing stuff relies heavily on knowing the round-trip time, the RTT. How does SRT figure that out?
It uses the ACK messages and something called ACK
Yeah,
messages.
ACK, ACK, an acknowledgement of an acknowledgement.
Exactly. When the receiver sends a standard ACK, the sender immediately replies with an ACK, basically saying, yep, got your ACK.
Hmm.
The time it takes from the receiver sending the ACK to getting that ACK back, that's the RTT.
Ah.
The receiver calculates this and includes the measured RTT value in those full ACK packets it sends back periodically.
So it's like a little ping pong game just to measure the network delay. Clever.
It is. And finally, SRT also handles drift management. Over long streams, clocks on different machines can drift apart slightly.
Yeah, happens.
SRT uses timestamps in the packets and some correction factors to manage this drift. Keeps the buffers and timings accurate and synchronized over time.
So SRT's reliability isn't about absolute 100% guaranteed delivery like a file transfer protocol might aim for.
No.
It's about guaranteeing delivery within a strict time window needed for live content, using smart buffering and fast retransmissions as the tools.
That's a really good way to put it. It absolutely prioritizes timeliness for the application layer above everything else.
Okay. Now, before any of this data actually starts flowing, the two ends need to connect and agree on all these rules.
Right.
That's the handshake part, right?
Right. SRT is connection-oriented.
Right.
Always starts with a handshake.
Mm-hmm.
The source material details two main versions. There's HSV4, that's the legacy one, based on the original UDT handshake, plus some separate SRT extensions stacked on.
Okay.
And then there's HSV5, the integrated handshake. Came later.
Why the move to HSV5? What was wrong with the old way?
Well, HSV4 was a little bit clunky for live use cases. It would do the basic UDT handshake first, get the connection technically up,
Yeah.
and then it would exchange all the important SR2 specific parameters, latency settings, encryption details, stuff like that, using separate messages after the connection was already established.
Oh. So you could potentially start sending data before you'd fully agreed on how to handle it.
Exactly.
Yeah.
Initial packets might go out before the settings were fully locked in. Could cause weird issues. HSV5 fixes that.
Ah, so HSV5 integrates all that negotiation into the initial handshake sequence itself.
Precisely. All the essential parameters get exchanged right there in the core handshake messages. So when the HSV5 handshake completes, both sides know exactly how they're going to talk. What version, what latency, what security settings, all agreed up front.
Makes sense.
The source also mentions HSV5 clients are smart enough to fall back to HSV4 if they happen to connect to an older HSV4 peer.
Good for compatibility. Okay. And how do these handshakes work for the different ways you can connect? Like caller listener versus that rendezvous mode.
So caller listener is the straightforward one.
Yeah.
One side is a listener, just waiting on a specific port. The other is a caller, initiating the connection to that listener.
Right.
The handshake generally has two main phases, induction and conclusion. The induction phase usually involves this cookie exchange. The listener sends a unique cookie.
A random number.
Yeah, basically. The caller has to reflect it back.
Sounds like a basic check, like proving you received the first message, maybe some DOS protection.
Exactly. Prevents simple reflection attacks before committing real resources. Then comes the conclusion phase. In HSV4, this was mostly just a confirmation. But in HSV5, this is where the good stuff is exchanged.
Like what?
The conclusion message in HSV5 carries key info like the protocol version being used, flags for features like TSBPD enabled or TLP-KT drop, and most importantly, the latency Y parameter negotiation.
Okay, so HSV5 packs all the SRT goodies right into that second handshake step. How is latency actually agreed upon in that HSV5 exchange? That seems critical.
It is. In HSV5, during the exchange of HSREQ, HSRSP messages, handshake request response, each side states the minimum received latency it requires the other side to use when sending to it.
Okay, so I say what delay I need for incoming packet.
Right. And the effective latency used for sending in a particular direction ends up being the maximum of the two values proposed for that direction.
Maximum, why?
It's a negotiation where the more conservative request wins. The higher latency value provides a larger recovery window, making the connection potentially more stable if one side needs more time.
Oh, okay. The safer value wins. Got it. What about rendezvous mode? That sounds trickier. Both sides trying to connect at once.
It is a bit more complex. In rendezvous, both parties are acting as both caller and listener simultaneously. They both initiate connections to each other on the exact same port.
How does that even work?
They both send out initial handshake messages, like a wave a hand message, kind of shouting into the void, anyone there?
Yeah.
When they receive the peer's wave hand, they know they've found each other and can move to the conclusion phase, eventually reaching an agreement state.
So they're both trying to call each other at the same instant. How do they sort out who does what next in the handshake? Seems like they could get stuck.
This is where the HSD5 rendezvous handshake has a particularly neat trick. The source calls it a cookie contest.
A cookie contest? Seriously?
Yeah. Both sides generate a unique cookie based on things like their IP address, port number, and the current time. They send these cookies to each other.
Okay.
Then they compare the numerical value of the cookie they received from the peer with the cookie they generated themselves. The party whose generated cookie value is greater wins the contest.
Wins what?
Wins the right to be the initiator for the rest of the extended handshake parameter exchange, like sending the HSREQ first. The other side becomes the responder.
Huh. A cookie bake-off to decide who leads the dance. That's actually quite clever. An arbitrary but consistent way to break the symmetry.
Makes sense, right? And just like in the caller-listener HSV5 mode, this designated initiator and responder that exchange all those crucial parameters, version, flags, latency for both directions within that handshake sequence using those HSRSP messages.
And this handshake phase is also where the security stuff gets sorted out.
Yes, absolutely. The keying material exchange happens here too, using KMM messages, KMREQ, and KMRSP. This is how the encryption keys get securely shared, assuming encryption is being used.
Right.
The handshake negotiation phase confirms the final security state. It'll report back if the connection ends up as no secret or unsecured, maybe because passwords didn't match, or bad secret if the password format was wrong, or hopefully secured.
So the handshake isn't just a simple, hi, can we talk? It's this really complex negotiation. Okay, how are we going to talk? What version? What rules? What's the latency budget? How are we securing this? All before the first bit of actual stream data flows.
Precisely. It's setting the stage very carefully for that very specific kind of conversation. Time-sensitive, reliable enough for live, and potentially secure.
Okay, let's dive deeper into that security piece then. The source mentioned built-in encryption. How does SRT actually secure the stream data?
SRT uses AES encryption.
Oh.
Specifically AES in counter mode, or AES CTR.
Okay. AES is pretty standard, strong encryption. Why counter mode?
AES CTR is well suited for streaming data. It turns the block cipher, AES, into a stream cipher. It doesn't require padding data blocks to a specific size, and importantly, if one bit gets corrupted in transmission, it only affects that one bit on decryption errors, don't cascade and corrupt the whole stream.
Makes sense for video. What part of the packet actually gets encrypted? The whole thing?
No, not the whole thing. It encrypts the data payload. The actual video or audio bits being sent. The SRT header itself is not encrypted.
Why leave the header unencrypted? Seems counterintuitive.
It's actually necessary for how AES CTR works here. Information in the SRT header, specifically the packet sequence number, is used as part of the counter value that gets encrypted by AES to generate the unique key stream for each packet.
Ah, so the header needs to be readable to know how to decrypt the payload correctly.
Exactly. The sequence number ensures each packet's encryption is unique, even if the data was identical.
Okay, header's clear, payload encrypted. How are the actual encryption keys generated and shared between the two ends?
SRT uses a neat two-layer key system. There's a short-lived key called the SEK stream encrypting key. This is the key that actually encrypts and decrypts the data payload packet by packet.
Okay, SEK does the heavy lifting. What's the second layer?
The second layer is the KE key encrypting key. The SEK itself is never sent in the clear. Instead, it's wrapped or encrypted using the KEK before being sent across the network.
And where does the KEK come from? Is that shared manually?
The KEK is derived from a shared secret. This is usually the password or passphrase that you configure on both the sender and receiver ends. It uses a standard function called PBKDF2 password-based key derivation function 2. This function takes the shared passphrase, mixes it with a unique random value called a salt, which is exchanged securely in the handshake's KMM messages, and performs a set number of computational iterations, basically making it slow and hard for attackers to brute force guess the password. The output is the key.
So the process is password plus salt plus PBKDF2 equals key. Then the sender generates an SEK, encrypts the SEK using the key K, and sends the wrapped SEK in a K1M message during the handshake.
You got it.
The receiver does the same PBKDF2 calculation with the password and the received salt to get the same key, then uses that K to unwrap the SEK it received. Now both sides have the SEK to encrypt the data stream.
Exactly. That wrapped SEK is what's passed in those KMREQ or RSP messages we mentioned earlier.
Clever. How does SRT handle changing keys during a long stream? You wouldn't want to use the same SEK forever, right? The security best practice is key rotation.
Absolutely not. SRT has a built-in, pretty seamless key refresh mechanism. It uses the concept of odd and even keys.
Odd and even.
Yeah. Periodically, the default is quite often, like every 2 to the power of 25 packets, which is a lot, but ensures rotation. The sender generates a new SEK. Let's say the current one is the even key. It generates a new odd key.
Okay.
Now, before the switchover point, the sender starts pre-announcing this new odd key to the receiver. It sends the new key, wrapped by the KEK, and KLM messages for a certain period before the actual switch happens. The default pre-announced period is 4,000 packets ahead of time.
So the receiver gets the next key well in advance of needing it.
Exactly. It has plenty of time to receive it and wrap it with the KEK and store it ready to go. When the sender hits the predefined switch point based on packet count, it simply starts encrypting packets with the new odd key and marks those packets with an odd key flag in the header.
Ah.
The receiver sees the flag change, already has the odd key ready, and seamlessly switches its decryption process to use that key. No interruption, no dropped packets due to key mismatch. The old even key is then discarded. Then the cycle repeats for the next even key.
That's a really slick automatic key rotation system baked right into the protocol.
Very cool. What did the source material say about security considerations or maybe limitations of this built-in encryption?
They brought up a few good points to be aware of. For instance, backward and forward secrecy. If you have a security requirement where someone who joins later shouldn't be able to decrypt past traffic, or someone who leaves shouldn't decrypt future traffic,
Yeah.
then relying solely on this in-stream key distribution isn't enough. You'd actually need to change the underlying shared secret, the passphrase, whenever membership changes.
Right, because the KEK derived from the old passphrase could still unwrap keys used during that time.
Exactly. They also mention that point about not encrypting the SRT headers. Paradoxically, they argue it can be a security benefit.
Because if you have predictable content flowing inside, like MPEG-TS video, which often has a sync byte 0 by 47 every 188 bytes, encrypting the headers might actually create recognizable patterns in the encrypted headers that attackers could potentially exploit using known plaintext attacks. Leaving the somewhat predictable header structure unencrypted avoids creating those potentially exploitable encrypted patterns.
Wow. So leaving a predictable pattern unencrypted is actually safer than encrypting it in this case. That's really counterintuitive.
It is. It makes you think. They also recommend disabling the encryption entirely if your actual input stream becomes highly predictable for a period. Like if the video is paused on a still image or it's just showing black screen or audio's muted.
Wow.
Because encrypting static or highly repetitive input can also create output patterns in the encrypted stream that might leak information or be easier for an attacker to analyze. Better to send unencrypted predictable data than encrypted predictable data.
Fascinating. And of course, they mention the fundamental challenge is always how you securely store and distribute that initial shared password or secret in the first place.
Always the hard part with symmetric keys.
Did the source mention any specific limitations to this built-in encryption? Situations where it might not work well?
Yeah, one specific scenario highlighted was trying to route an encrypted SRT stream through some kind of intermediate device or proxy that needs to terminate the SRT connection and then reestablish a new SRT connection to the final destination.
Like a relay or a gateway.
Exactly. Because the SRT sequence number, which is crucial for the AES-CTR decryption counter, is unique to each specific SRT session. If an intermediary receives an encrypted stream, decrypts it, assuming it has the key, and then tries to re-encrypt it for a new SRT session going forward.
The sequence numbers will start over or be different on the second leg.
Precisely. The sequence numbers change. The final receiver wouldn't have the right sequence numbers corresponding to the original encryption counter, so it wouldn't be able to decrypt the payload correctly. It would require a really complex system on that intermediary to somehow map sequence numbers across sessions and manage the key material appropriately.
Ah, okay. So the built-in encryption is really best suited for direct point-to-point connections, or maybe point-to-multipoint where the source encrypts once. Not ideal for complex routing paths involving multiple SRT hops that terminate and restart the session.
That seems to be the difficulty the source points out. If you needed security across multiple hops like that, you might be better off using application layer encryption before the data even hits SRT.
Got it. Okay, so beyond the core reliability, low latency, and security features, did the source mention any other notable SRT capabilities?
Just a couple quick ones, yeah. It supports configurable congestion control, or CCC.
We touched on UDT's congestion control being bad for live.
Right. SRT's default live mode is specifically designed differently. It tries to maintain the target rate and prioritize low latency, even if there's some network congestion.
Yeah.
But the source notes it can support other congestion control algorithms. They mention a file mode, which would presumably behave more like UDT's original bulk transfer approach, maximizing throughput.
So you're not totally locked into one strategy, though live is the default and main purpose?
Correct. And crucially, the specific congestion control algorithm being used has to be agreed upon by both sides during the HSV5 handshake. They have to match.
Makes sense. Anything else?
And finally, there's something called the stream ID, or SID.
SID.
Yeah, it's basically an optional string of text, up to 512 characters long. The caller can send this string to the listener during the HSV5 handshake.
What's the purpose of that?
It's mostly useful for the listener side, especially if it's a server that might be receiving connections from many different callers on the same port, or maybe a server that can send different content streams back. The SID allows the caller to identify itself, maybe say, I'm camera feed 3, or to request a specific resource from the listener, like, please send me the main program stream.
So it adds a layer of addressing or identification on top.
Mm.
Useful for more complex server setups.
Exactly. The source notes it's not typically intended for use in rendezvous mode, more for the caller-listener scenario.
Okay. Wow, that was a seriously deep dive into SRT. We really pulled it apart.
Yeah, quite a bit there.
We looked at its roots, understanding why UDT wasn't quite the right fit for live video and how SRT fundamentally adapted those reliability mechanisms. Moving to millisecond buffers, those periodic NAs, timestamp-based packet delivery, and that really key idea, the willingness to drop old packets for timeliness. We saw how it balances that reliability with low latency using buffer management and timely retransmissions, all dictated by that RTT-based recovery budget.
Right, the latency setting is the budget.
We untangled the whole handshake process, too. Appreciating the jump from HSV4 to the integrated HSV5, and the different dynamics of caller-listener versus rendezvous, including that fantastic cookie contest.
The cookie contest is memorable.
Definitely. And we detailed the built-in AES-CTR encryption, the clever odd-even key rotation, and some of those important security considerations and limitations, like handling intermediate hops.
It really does lay bare just how much complexity goes into making something seem simple. Like getting a smooth live video stream across the messy, unpredictable internet.
Yeah, it makes you appreciate all the engineering happening silently in the background whenever you watch a live concert stream or hop on a video call that actually works well.
Absolutely. And, just think about that handshake process we walked through again for a second.
Okay.
The induction, the conclusion, the different versions, the caller-listener versus rendezvous modes, that cookie contest, just to decide who leads the next step. And then that asynchronous back and forth exchange of all those critical parameters. Latency settings specified for each direction. The secure exchange of wrapped encryption keys. It's really quite remarkable, isn't it? All that intricate negotiation and agreement happening in fractions of a second, just so two machines can figure out how to talk reliably and securely across the vastness of the internet before even the first byte of your actual video starts its journey.